I have wires hanging from me, so I'm a little bit worried if I can step left and right. So welcome to this talk on HTTP2. My name is Hadi. I work for a company called JetBrains. Have you heard of it? Yeah. Brilliant. Do you like it? Yeah. Okay, good. If you don't, well, tough. You're still stuck with me for this talk. So what is this? This is a talk on HTTP2. And what we're going to see is basically what you need to know as developers to deal with HTTP2 and how it impacts you from a perspective of developers or from IT or what have you. Now, how many of you are actual developers here? Pretty much everyone. Anyone that is not a developer? Okay. But somehow related to web. Good. Okay. So this is more or less about web. So if you're not doing web, probably not the talk for you either. And what I'm going to show you is basically an overview of HTTP2 and what, in essence, how it impacts our line of work. Okay? If you've done any HTTP2, this is again probably not the talk for you because you'll probably know everything that I'm going to say. Right. Given that disclaimer, let's start. The World Wide Web in 1996. Who remembers it? It was fantastic. And back then we used to have a thing called Yahoo. Well, we still do. I checked today, it's still around. So we had this thing called Yahoo, and it was fantastic because basically it was a web page where you would go, and every web page would have just text, and some of those texts would go to links, and then some of those links would do something, and then you would go to another page, and it would have a bunch of more links, and it would do something else, and it was fantastic. It was brilliant. Back then, we didn't have things like Stack Overflow, where everyone now is a developer because of Stack Overflow. We had Deja News. So you were a developer because there was Deja News. Have anyone used Deja News? I'm going like way back. I'm showing how old I am. And of course, the thing is that back then also, in terms of internet users, we were much, much less. So you can see that, you know, back in 1993, there was very, very few internet users. Right now, we're about 3 billion. Probably 1 billion of them are on Facebook, unfortunately. But there was less people, and it was good in a sense. Everything was great. Nowadays, you know, there's more people, and if you look at users by country, we can see that that's more or less the distribution. And there's a lot of people in Asia. So, like China makes up a lot of the internet. There's a tiny little thing there in green, which is called Oceania, which is Australia. Anyone from Australia here? Right. It's extremely, extremely slow, the internet there, which probably explains why there's very few people there as well. That's our distribution. And nowadays, we have better user experiences and visuals. We've gone away from those pages that we used to have, which was basically just text with HTML and links. We've got much better visuals. Some are more or less the same still. They've just got more images. But overall, the experience has improved. And I was looking at websites to see like how this actual experience has improved. And I went to a website which was called Let's Find a Doctor. It was by a company called Fantasy that had won an award. So I just Googled it. I said, the best website in the world, and Fantasy came up. And it took me to here. And basically, this was a website where you can choose your doctor. So it's kind of like Yelp, but for doctors, if that could exist. It does. And what you do is you can like say, you know, I go to a website, I've got this illness, who are my doctors? I can go find the doctor. It tells me the best path to the doctor. I can look at the doctors, see what kind of timetable they have, if it matches my needs, look at their reviews to see what kind of reviews there are, and based on that, choose who I want to go and put my life hands in my life in their hands. Talking about that and talking about reviews, how many of you have heard of a company called Fake? There was an article some months ago from a company, or it was an article by a journalist that had created a company called Fake, which stood for Freaking Awesome Karaoke Entertainment. And basically they had become the most popular, best awarded, best reviewed company in the world for karaoke's, but it never existed. Point being, take all of these reviews with a pinch of salt, whether it's doctors or restaurants. But that is a beautiful user experience. Yes, we all agree with that. And it's all smooth. Everything runs very, very well. Everything's great. We've all got more bandwidth. By and large, you know, I've got 300 megabit fiber optic coming to my house. I'm on Wi-Fi, so I only get like 80 megabits of it. But 300 megabits, I could do anything I could dream of, even Netflix. And everything is great. Back in 1984, there was a chap by the name of Jacob Nielsen who predicted what was called the law of bandwidth, which is kind of similar to Moore's law, which we eventually ran out of. We reached the peak of Moore's law. And he predicted that overall, year by year, there was going to be a growth of internet bandwidth. And he was more or less accurate. You know, everyone's got a good bandwidth. Yeah. If we do a breakdown by country, we can see that there are, you know, South Korea is at the very top with something like 25 megabits per second. Right at the bottom, we have Bolivia with 1.1. You've got the US somewhere in there, Spain, which is where I'm from. That's a lie. It's not 7.8. I don't know who they hold there. But, you know, overall, things are good. Yes? You've all got good bandwidth. Yeah? Okay. Even mobile's got good bandwidth. I'm not so sure about the US. I don't know if that's accurate. But overall in Europe, more or less, you get good bandwidth. So, you know, Europe, you get 20 megabits. Some people don't even have a landline anymore or a fiber. They just use mobile. So it's all fantastic. Everything is brilliant. It's all good. So given that, why are we dumping HTTP 1.1? Why HTTP 2? What's the purpose? If everything runs smooth, we've all got brilliant bandwidth, why are we dumping? So my theory is because we need to keep our industry self-sustaining. So we've got to come up with new things to kind of like justify this conference and training and talks and consulting and all that. But that aside, conspiracy theories aside, which is true, the problem isn't the bandwidth, right? The issue isn't the bandwidth. The issue is the latency. Right. There was a paper back in 1996, I believe, by Stuart Cheshire that said, it's the latency. It was titled, It's the Latency, Stupid. And he predicted that the issue isn't going to be bandwidth, but it's going to be latency. And just to get everyone on the same page, what's the difference? Bandwidth is, let's say I have a highway, it's how many carriageways I have on that, how many lanes I have on that highway. Depending on the number of lanes, more cars fit, I can do more, do less. Latency is how long it's going to take me to get from one point to another, right? So effectively, what is the speed that I can reach? And what is latency limited by? Speed of light, right? So latency in a fiber optic, actually that's a lie, because 3 days ago, I read an article which a university in UK has managed to accomplish more than fiber optic speed by multiplexing multiple fiber optics together. But anyway, for now, let's just assume that it's limited by the speed of light, which it is. So in a vacuum, the speed of light has a specific speed, but we don't live in a vacuum, nor do our cables. And in between these cables, we have intermediate objects. We have routers, we have switches, we have other cables, we have computers, etc. And all of these add their own delay. They add their own latency. So we don't get the speed of light. We get something much lower. Now, what that means is that, for example, if I'm in Frankfurt and I want to ping somewhere in New York, it's going to take me something like 150 milliseconds to get from one point to another. Now, let that just sink in for a second. Okay, 150 milliseconds. Is that fast? Apparently not. Apparently not. It's fast for me, right? But apparently not. There has been studies that have proven that if a page load takes more than 10 seconds, people will go to your competitor. If a page takes more than 3 seconds, people lose attention span, right? I blame Twitter partially for that. But the reality is that apparently we have become so short on attention span that if we take more than 10 seconds to load a page, we've lost potentially 6% revenue. So it all boils down to money. And this is done by studies by all of those big companies that generate products and sell products and have cloud services, which I won't mention. But potentially, that is an issue. So realistically, if we think about it, 150 milliseconds, that's just crazy. Back then, when I started with the internet, I used to be able to like go to the kitchen, grab my coffee, come back, and the page loads, and I was happy. And nowadays, with 150 milliseconds, we're like, this can't do. We need to find better. Okay, well, we just did. It's called HTTP 2. Yay, good for us. But that is the reality, right? So we need to do better than 150 milliseconds. Now, in my case, for example, in Spain, that's not true because we don't have competitors. If something's slow, we just put up with it. Here is a breakdown of bandwidth and page load time. So as you can see, as the number of, as the bandwidth increases, there is a drastic drop in page load time, but it gets to a point where there isn't anymore, right? It just starts to become just a little bit less, but not significantly. Here is charts showing the latency per bandwidth and page load times or return trip time based on bandwidth, again. And you can see that there is an increase, but it reaches some point where there isn't. So this is problematic because the latency is an issue. But there's a bigger issue, which is the latency is per connection, right? Now, back in the old days, when I showed you that Yahoo page, you would go to a server, you would open that page, it would dump everything back at you, and it would be all awesome. It was a single connection. It was fantastic. This is the Google Chrome output of a newspaper in Spain, right? And it takes me literally 1 minute for that page to load. It's a newspaper, 1 minute. Now, fortunately for me, the contents I'm interested in, which are the articles, takes about 15 seconds. The rest of the time are the adverts, right? But that's the reality we live in. We are bombarded with ads, and the page load times takes a lot. But look at how many individual connections that is opening, right? For a page load, it is opening like hundreds of different connections to different things, to different resources, right? One get is causing like 300 more gets. And that is an issue when we're talking about latency, because each get could potentially be its own connection. If we do a breakdown of the actual time that is being spent, we can see that, a lot of it is just waiting, resolving host, wait time, initial connection. Look at that yellow, the orange part. That is the initial connection. So out of like 10 milliseconds to say, 8 milliseconds is actually going into the connection. And 2 milliseconds is everything else. How many of you know this page, which is called Web Page Test? So you go to it, and it gives you beautiful diagrams, waterfall diagrams, of how long a page load takes. And the issue is, that it's called a waterfall because is an underlying TCP, which we'll see, it just kind of causes delays. X blocks are processed, and then the other X blocks are causing delays by those ones, and as it progresses, it goes down. And you can see that a lot of time is just wasted. Now, that isn't the problem so much for HTTP as it is the network. So the ISO of the OSI, right, the layers of the OSI, goes back down a little trip down memory lane. Who can tell me where HTTP sits on those layers? Yes? Pardon? At the top layer, application? Yes? No? Transport? Yes. No. So HTTP is an application protocol, oftenly confused by transport protocol. No, it actually sits at the top. It's the application layer. So that sits at the top, and under it, there is this other thing called transport, and below that, there's a network, and then the link, and then physical. But everything on TCP, which is what HTTP runs on transport, right? And guess what? Transport, by defect on the internet, is more or less TCP, or in the case of our HTTP, it's TCP. It doesn't run on UDP, and TCP has issues. It has a lot of issues, like serious issues. Here's a simple echo server. So this is a server where I send a hello to, and it responds with a hello. Look at all the packets going back and forth. For just a simple hello. Why? To begin with, HTTP has what's called the three-way handshake, right? So before establishing a connection, on establishing a connection, before actually exchanging data, I have to say hello, and you say hi, and then I say, okay, I've received your hi, now let's start to talk. So every time I initiate a new TCP connection, which means every time I initiate a new HTTP connection, I open a TCP connection, I got a three-way handshake. Guess what I do when I close a connection? Another three-way goodbye. And then for every connection, I'm sending back data and forth because TCP is reliable. So it requires certain packets to be sent back and forth. So already we're adding a whole bunch of time. So I can say, for example, I initiate a connection that sends 90 milliseconds, out of which 80 milliseconds of it is just a handshake. On top of that, TCP has another issue which is called flow control. So let's say I have a server here and I have another server here, and these two machines want to talk together. Okay? Fantastic. I've got a 100 megabit cable between them, they talk at 100 megabits. But that's not the reality of the internet. The reality of the internet is that we have multiple machines in between. And each of these machines have their own congestion problems. They have their own bandwidths. They have their own buffers. They've got all of these different issues. So the way that TCP, to not congest some intermediate solution, some intermediate server, the way that it works is by this mechanism called flow control. So when TCP starts to transmit data, it says, I'm going to start with 100 bytes, let's say. And then the server says, okay, I've received your 100 bytes. It says, okay, great, I'm going to increase the window and I'm going to send you 200. And then it sends 200. Now I'm going to send you 500, 500. Now 1,000. Oop, I'm suffering congestion. Okay, let's bring it down back to 800. So this is called flow control. And TCP on top of that is affected by this thing called flow start, which effectively means every connection starts with a small window, a small buffer, and it gradually increases in size to avoid congesting the network. And of course, what happens now? Every time I open an HTTP connection, which opens the underlying TCP connection, it's affected by slow start. So if I want to send 100 bytes, I might be okay because the window is 100 bytes. If I want to send 4 megabytes and the endpoints can do with this, I'm still going to go through that slow start to build up that optimum bandwidth. So that is another issue that TCP has. And it's not an issue. It's just the way that it's designed to deal with avoiding certain things like congestion of the network. Now, as I said, back in 1991, we had HTTP 0.9, which was really simple. I did get index.htm, and it sends back text. What's missing there? Can someone tell me? Headers. We had no headers, and it was awesome. It was simple. We didn't, back then no one was saying that if you send back JSON, you're doing REST. And nobody cared about unpretty URLs because everything was pretty. Then came HTTP 1.0, and it said, I'm going to bring you headers and start to complicate things. I will give you a user agent, and then you can send headers, and you can get headers back. I'm half joking. It gave many possibilities. It provided us with content type representation, so now I could have text.html, or application/JSON, or what have you. But there was still an issue. Every time I opened an HTTP connection, it would open, get the resource, close, right? So each connection, each get was suffering slow start, was suffering three-way handshake, was suffering three-way goodbyes. HTTP 1.1 came around and introduced a new thing, which was called the connection header. And by default, it left it open, meaning that now I could actually send multiple requests on a single TCP connection. So I would open up an HTTP connection, it would remain open. So I saved on the slow start, I saved on the three-way handshake, and I saved on the three-way goodbye. And that gave way to new optimization techniques. As I said, I had a single connection. I could open up a connection to a server, get the index, then get the style.css, everything. So we tried to take it one step further. Here what I'm doing is I said, index, give me back index. New request, style, give me back style, right? Then we tried to introduce this technique called HTTP pipelining. How many of you have heard of that? right? With HTTP pipelining, we said, what if instead of me sending all these requests on the client one by one, what if I pipeline all these requests on the server and then get the server to just pump it all back to me, potentially even doing parallel processing? And that was, in theory, that was an awesome idea. In practice, it never worked because HTTP suffers from an issue which is coming from the underlying TCP, which is called head-of-line blocking. How many of you have heard of that? So TCP is a reliable protocol. For it to be reliable, it needs to kind of track what packets are going back and forth, in what order they're going, if there's a packet dropped, etc. So it can potentially block whatever is coming next until the previous things have been solved. And therefore, that's bubbled up to HTTP, meaning that even if I sent multiple requests pipeline on the server, if one request wasn't processed, the ones behind it wouldn't be processed. So it wasn't causing many improvements. But what we did do is start to exploit the concept of connections, and we opened up with multiple connections. So we use multiple TCP connections to perform parallel requests, right? I open up a connection, I do multiple requests. Problem is, the browser said, whoa, I'm limiting you to 6 connections per host, 6 or 8. And we said, you're gonna stop me? No. We invented this other thing called domain sharding, which said, see, the thing is that the browser limits by host name. We said, okay, we'll create an alias pointing to the same server, but now we've got more connections going to the server. How many of you use domain sharding? Right, great. So a lot of things I'm going to tell you now, you're going to have to stop. But of course, domain sharding doesn't come free because it came with another thing which was called DNS lookups, right, which also impact the connection. And guess what? Even if we magically use a single connection, it still creates resource issues on the server, on the client, because we're opening up sockets, and sockets aren't free. So I have 100 sockets open to a specific connection potential, to one server. We tried to optimize a little bit more with other techniques. We introduced this concept called inlining of resources. So if I have an image, instead of doing an explicit get, I can inline that image. If I have some JavaScript, I can inline the JavaScript. If I have CSS, I can inline the CSS and then end up with spaghetti code, of course, but we tried to do it. But that also brings other issues. No cache usage, right? How many of you have actually done inline resourcing? Which basically means I can embed an image inside an HTML page. If you haven't, don't even bother. It's like smoking. If you're not smoking, don't start. And if you've done it, stop. Because apart from caching, because if every time I'm embedding that into the HTML page, it invalidates the cache, right? It also has encoding overhead, because of course I can't embed an image, I've got to do base 64 encoding of an image. We came up with additional techniques to try and solve this, concatenating and spriting resources. Now, concatenating is very beautiful. It's a process by which I have 30 different JavaScript files, and I use an overly complex build tool, which every month is a different flavor. I think this month it's Gulp, last month it was Grunt. And that creates a single JavaScript file for me. Woohoo, because I only get one request. Oh dear, if I change one function, I've invalidated the entire cache. Right? You do that still though, right? Because overall, hey, it might pay off. The other thing that we invented was spriting. Spriting is this fantastic technique by which I can take multiple images and create a single image and then spend 7 to 8 hours using CSS to try and position those images on the page. But hey, it saved on some issues. But of course, that also, apart from caching issues, brings other problems, which is delay in processing. If I have a single JavaScript file that's going back, if I have a single CSS that's going back, the page needs to load the entire thing before it can start to process. So all of these are problems. We try to hack our way around it. We introduce new problems. And all of this, why? Because the culprit is not HTTP, but TCP, right? HTTP 1.1 is a very chatty protocol. TCP is not made to be chatty. TCP has the slow start and the head of line blocking that we spoke about. So all of this is why we've come to HTTP 2. Okay? Now, if you're web developers, you've probably dealt with all of these things. That is why. So I spent a good 45 minutes telling you why we need HTTP 2, but it's a valid point, right? You know the 5 whys? Yeah? If they ask you something, ask 5 times why. If you have kids, you know how that works. Just lock them in a room. To sum up in one slide, it's about performance. HTTP 2 is about performance. In a few more words, HTTP 2 is a binary communication protocol. It's no more text. So gone are the days that we could do a telnet and watch that ASCII text go back and forth, which is beautiful. I love it, but it's gone. It's over. It uses compression and optimization techniques to try and improve performance. The good news is that there is no change in HTTP semantics. So get, post, put, content type, accept, all of these remain the same. Everything remains the same. In fact, it only introduces a couple of new concepts. But, of course, given that it's a text protocol on a binary, it's not compatible. So it's not going to work. Okay. Any questions, by the way, so far? You're awfully quiet. I'll take that as a no. So the next question is it speedy? No. But it was based on Speedy. How many of you use Speedy? Probably everyone in this room uses Speedy. They just don't know about it. How many of you use HTTP? 2. Right. How many of you are on Twitter? Right. Everyone on Twitter uses HTTP 2. You just don't know about it, which is great, right? We've abstracted it away. Well, Twitter has. Is it Speedy? No, but it's based on Speedy. So Speedy was an effort by Google to try and improve performance and speed of the web. And it was used for many years, and other companies adopted it. And then when the RFC, well, the IETF got together to say it's time for HTTP v next, they put in a request for papers, and Speedy was submitted. So it's basically based on the same principles, ideas as Speedy. And then Google said, we're no longer developing Speedy. And in fact, in 2016, Google is dropping support for Speedy in Chrome. Okay. To look at it in a single slide, this is basically what it is. You have a mapping between text to binary. So I have my text HTTP, which is the get, the headers, and the response, mapping to a frame which has a header frame or multiple header frames and a data frame or multiple data frames. So the next question is, if one is text, the other one is binary, how the hell is this going to work? I mean, how can I use it? You're using HTTP 2 today. How? How are we using the existing infrastructure to use HTTP 2? And there are ways to do it. In fact, there's 2 ways. One of them is called H2C, or Clear Text Upgrade. And basically what happens here is that the HTTP protocol has this concept of upgrade. You can upgrade your protocol. So what happens is that the client sends an upgrade, H2C, which means HTTP 2 over clear text, and sends also some specific headers, which are HTTP 2 settings, and then the server says, yes, I can switch. If I can, it sends back a 101, which stands for switching protocols. And then from there on, it switches to HTTP 2. Now, everyone understand this? Yes. Forget it. It's never going to be used. Why? Because the majority of browser vendors have said, we don't want to implement HTTP 2 over clear text. We want everything to be SSL. Of course, that was before they hacked SSL. But they said, no, we want everything to be SSL or /TLS, which is the same thing. It's based on the latest of 3 of SSL. And so we want to use SSL. So really, effectively today in the browser, if you're using HTTP 2, it's using HTTPS. It's going over TLS. And the problem was with TLS is that TLS has its own handshake. So it's costly. So now I've got the TCP handshake, I've got the TLS handshake, and now you're saying to me that it's not going to be over TLS, but it's a new protocol, which is HTTP 2, so I've got to have another protocol handshake on top of that, go away. So what they did is they invented this thing called ALPN, which is an extension to TLS, which stands for Application Layer Protocol. What's the N for? Come on. There you go, negotiation. And what that does is allows you to inject into TLS and say, I want to use TLS, but to switch to a new protocol. Today it supports HTTP 2. Tomorrow, because our industry keeps revolving, we'll support HTTP 3 or 4 or what have you. And that's how it's used. So by and large, the majority of HTTP 2 nowadays is on HTTPS, which again is a good thing, because if we move to a secure web, it's great. It's going to be a very, very bad problem for the United Kingdom, because they're trying to make encryption illegal. You know, like how in the old days you weren't allowed to export stuff from the US, so people used to go with PGP algorithm printed on a T-shirt. Those were the days. So the UK has said, we want to go down that route. Obviously, they won't be able to make it because Apple will stop them, but anyway. So that's basically how we use HTTP 2 over HTTP 1.1. Now, one other important aspect of HTTP 2 is that it's a single connection. You no longer open multiple connections to your server. You just use a single connection. But inside that single connection, what you have are streams. So you can have multiple streams. And inside those streams, you have frames. So you have header frames, data frames, connection settings frames, upgrade frames, a whole bunch of different frames. What is a frame? It's basically composed of different bytes. It's all binary, so it's much easier to decode. That's why they did it with HTTP is binary, because it's much faster to do encoding, decoding of binary than it is with text. Why? Because text requires decrypting, encoding, and decoding. But on top of that, people mess up with text. They insert line feeds where they shouldn't. If you've ever implemented MIME, you'll know how horrendously bad idea text is. So this is binary. So every frame has a length, it has a type, it has a flags, it has an ID. ID, that's really, really important, and we'll see why. And then it has the actual data. There's different types of frames. There's a data frame, which is where all the chunk of the data is going back and forth. There's a header frame, where the headers are being sent back and forth. There's a window update frame, which is ODME. We've just introduced a low-level concept to TCP, to HTTP, which is flow control. We'll see in a bit. There's a whole bunch of different frames. So this is all binary. How do I see it? You use Wireshark. How many of you use Wireshark? This is the new telnet. Get used to it. If you want to do HTTP decoding, encoding, you start to use Wireshark. There's other tools as well, but Wireshark works well. If you've ever configured Wireshark to work with SSL, basically the same concept. You dump the browser key file, SSL log, to a folder, and then you configure Wireshark to read off of that folder, and away you go. So here, you can see a whole bunch of data of the different frames. Here's what a data frame looks like. It's beautiful, isn't it? Really fantastic. Like, if you love HTTP, this stuff is like, oh, it's amazing. So, I know, I'm weird. Now, one thing that is important is that there's proper multiplexing. So multiplexing, you all know what it means, right? It means use a single channel to send multiple things, and then on the other side, demultiplex. And that is the key thing here. That's why HTTP only requires a single connection, because it can send multiple requests and responses in parallel, concurrently. And because it has proper multiplexing, you don't have to worry anymore. You don't have to open up multiple connections. So I can have different responses going back and forth, and the protocol takes care of sending that to me in the right order. I no longer suffer the head of line blocking that I suffered when I tried to do the pipelining with HTTP. It's bidirectional, and that ID is what allows us to have proper multiplexing, because each frame has an ID, so I can find the ordering, etc. So that's a good thing. What are the things that HTTP 2 bring? This is two headers of two resources on GitHub. If you look closely, which you can't because it's too small, but if you look closely, everything is pretty much the same except a couple of bytes. And yet, every time we send the request, we're sending all of these headers forward and all of these headers back for 4 or 5 bytes to change. So HTTP 2 tries to address this problem as well. How? By introducing header compression. And it uses this thing called HPAC. Initially, it used zlib, and then they hacked it, so they switched over to this other thing called HPAC. And it's basically Huffman encoding for encoding the headers, and it uses some virtual tables to say what has changed, and then sends back deltas back and forth in the connection to only send back what is changing. making it much more efficient in terms of data going back and forth. But all of these streams now introduce other things. They introduce these concepts of priorities. So HTTP2 gives us a lot of benefits, but it also gives us a lot of control in many other things. And it says, you can have priorities. Since I've got concurrent streams going back and forth, since I can have multiple requests going back and forth, why don't you give them priorities and tell me if you want HTML with higher priority over JavaScript, if you want JavaScript with higher priority over CSS, if you want images to be lower priority, and it allows you to do this. So now each stream has a priority, and we can define how we want these priorities to go back and forth. Now the problem with this is that each stream in turn, let's say for example, I have a stream that is getting me some JavaScript, and that JavaScript in turn has another dependency, right? So now we got these complex dependency graphs of, we get the kind of the same thing here, all those dependency graphs, right? Fortunately, we don't really have to deal with these things, fortunately. Unless you want to do low-level stuff, which we'll see later, you don't need to deal with this because this is more handled by HTTP server implementations. What it also provides us is flow control. So the same TCP flow control that we saw, again, if I have multiple streams going back and forth, I can potentially congest something because I can have, for example, a stream that's doing some database processing versus another stream that's just streaming out video, and one could potentially cause a bottleneck for the other because it saturates the socket for whatever reason. So it allows you to also do flow control management. So what it's doing is giving you a lot of benefits, but it's creeping up a lot of the lower level stuff higher up to the application layer. One really good thing that it introduces is called server push. And the idea behind this is that in a normal request, I do index.html, and it comes back with style.css because the index.html is giving me a request to style.css. The browser parses it and says, oh, I need style.css, oops, I need script.js, so it's going to send these requests to the server, and the server is going to respond. What server push allows me to do is say, oh, you're asking for index.html. Before you even request script.css, I'm going to push it to you. Before you even request style.css, I'm going to push that to you. So it's preemptively sending data back to the client, right? That's quite good because it saves on a request response. Well, not on the response, it saves on the request. It saves on waiting for the server to issue a request. The caching works exactly the same. So the question is, how does that work with caching? Different to inline resourcing, it's still a response that's going back. And the client has ultimate control over what it wants to do. So you can send back a push. If I do an index.html, let's say I do index.html, and then without using HTTP2, then you do a style.css, the server responds and says not changed. It could do exactly the same. It can say it's from the last request, it's not changed. So I'll send you back an HTTP 302 saying it's not modified, or 304 it's not modified. Okay. What this is trying to do is replace inline resources, basically. That's the idea behind it. And what happens is the server does what's called a push promise from the server, and it allows for caching, also for the client to be in control of this. So ultimately, the client can reject pushes, and the client can also cancel pushes. Okay? So ultimately, the client has control over server push. What HTTP2 also brings is security. And again, it's not forced. The HTTP2 protocol does not require everything to be encrypted, but by and large, as I said, browser vendors have said, we're going to encrypt by default. So TLS is implemented by all supported browsers, and by and large, you kind of lead to a more secure lifestyle. So what is the current status of all this? May 2015, the RFC was published on the 7540, and HPAC is also published alongside of it, 7541, which is the protocol for header compression. The good news is that unless you're doing low-level stuff, everything I just spent 45 minutes telling you about, you can forget about. You don't need to know. So you just wasted your time. That's the good news. No, that was the bad news. The good news comes now. Good news, I'm going to show you this. I'm going to show you this. How many of you know Can I Use? That was a joke, by the way. Anyway. Can I Use is a website that you can go to, and it tells you if you can use a specific technology, Ajax, JavaScript, etc. So you can notice here that pretty much all of the browsers already support HTTP 2. In fact, if you come here, this is Microsoft Edge. How many of you use Edge? Okay, so it's not really applicable. Keep forgetting this is a Java conference. If you use Microsoft Edge, it no longer even supports Speedy. So if you type in Speedy, Edge won't support Speedy. Now, this is browser support. What about server support? The good news is that you are Java people, the majority of you. And Java is actually very advanced in the HTTP 2 scenario. If you are .NET, you're really out of luck, because there isn't much support on .NET. Microsoft is coming with Windows 10 preview, and Windows Server 10 has support. But on the Java side, we've got so many options already. So we have Jetty with 9.3, we have Wildfly, Nginx, however you want to call it, IIS in Windows 10 and Server 2016, H2O, Akamai, Edge, and Apache 2.4. The issue is that, remember those ALPN things that I told you about, those are an extension that are required to use HTTP 2 if you're doing server-side or client-side in Java. And that's going to ship out of the box with JDK 9. Up to now, you have to include a jar in your class path, effectively. That's what that means. Okay, it requires some external ALPN extensions. Client-side support, we're good as well. Actually, I'm missing, well, client and server-side. Jetty, Netty, who uses Netty? It's awesomely low level, but it's awesome. And Netty has support for HTTP 2. Curl is a library, is also a command line tool that has support. That's more if you're doing C stuff. OK HTTP, which is a fantastic HTTP client for Java, that already supports HTTP 2. In terms of tooling, what do we have? Curl, as I said, Chrome tools, Wireshark, web page test, and NG HTTP 2. There's a whole bunch of different tools that already support HTTP 2. So let me show you some demos. And this is the best part, because this is where everything I've said proves false. I'm really not joking here. So let me displays, and does anybody see my mouse? This is so much fun. Okay, so let's go to Chrome, and I'm going to open up a new window, and I'm going to go to, let's see, which one do we have first? We have Akamai. Let's go to this one. So here is Akamai. And you see, if you come here with an HTTP 2 browser, it says, congratulations, you're using HTTP 2. And then you see, click here for a demo. And this is Latency loading HTTP 1.1. What it's doing is loading multiple images. It worked. Fantastic. Latency 0 milliseconds, load time 0.91, versus load time 3.93 and latency 94 milliseconds. And I'll just stop right there, because if I load this again, it'll probably give me the exact opposite. That's why it's beautiful. It randomly works, randomly doesn't. But the idea there is really true, which is what it's doing is loading many small resources. And this is where HTTP 2 shines. Instead of having multiple connections, multiple concurrent connections, it's just using a single connection to get all of those resources. Okay? So that works. Let's go to the other one, which is HTTP 2 demo. And you can see that that's a 1, and I run 2. And again, that also works, right? So there is a massive impact on performance when it comes to HTTP 2. Okay? Now, Chrome feature, which is nets. Never mind, I'll show it later, doesn't matter. Which allows you to see the exchanges as well, but we'll see it later. Anyway, so now the big question. We know what HTTP2, why it's come, what it is, what it provides, how awesomely fast it is, fantastic. How does that actually affect our applications? It doesn't, although it does. Mostly, it's transparent. What that means is that really, from a semantical point of view, you really don't need to do anything different. If you're talking to an HTTP2 endpoint, doing REST calls or HTTP APIs, it's not going to impact you in much sense. But let's first talk about web apps and how it impacts if I'm doing web application development. So Spring, whatever, what have you. So everything that you've been doing in terms of optimizing up to now, you basically have to undo. That's how it affects you. But it's great, right? We can still charge consulting rates. And what it does is you have to get rid of the multiple TCP connections. You don't need them anymore. Why? You got a single connection that allows concurrent streams. Why do I have multiple TCP connections? In fact, it's adding an overhead that I don't need. So all that domain sharding, all of that, yeah, roll that back. Domain sharding, roll it back. Concatenation and spriting, roll it back. Why? Because I've got a single connection. All the overhead of TCP is gone. I don't need it. But this is good to roll back. It's not good for all those people that invested years of their life in getting grunt to concatenate JavaScript files, but otherwise it's great because I get my caching back and I get my sanity back as well with it. So concatenation and spriting comes back. Goes away. Inline, bad idea. You've got server push. So you can undo that as well. Now, what about APIs? So from a web application point of view, fantastic. What about APIs? How does this impact my APIs? So, first of all, HTTP as a protocol itself hasn't changed, and HTTP2 hasn't. We still have exactly the same semantics, all the same. But now we don't have to worry about any more chatty APIs. So how many of you do HTTP API endpoints? Okay. How many of you do RESTful endpoints? Always, there's more people doing RESTful endpoints than HTTP2 API. How many of you use Hatios? Okay, so Hatios means hypermedia as the engine of application state, which is the requirement to do RESTful endpoints. Essentially meaning that probably the vast majority of us only do HTTP API endpoints. Except nowadays, unfortunately, if you do pretty URLs and you return JSON, they say it's RESTful because you use 4 or 5 verbs of HTTP. It's not the case. It's a lie. Trust me, read Roy Fielding's paper. It's a lie, but it's okay. No one's going to kill us for it. Except Roy. No, he won't either. So anyway, one of the problems that people, when they design these HTTP endpoints, they say, oh, well, this is a problem because I've got this back and forth chatty protocol, right? When I want to create a customer, that involves 7 or 8 operations. So I'm making 7 or 8 operations to my HTTP endpoint. And HTTP2 is going to solve that problem for me because now it's going to be on a single connection. Wrong. You shouldn't have been making 7 or 8 endpoint calls anyway. That should also be encapsulated on the server side. But if you are, yes, HTTP2 can solve that problem of chatty API protocols. So essentially here you're getting a free lunch because you really don't have to do anything and it's going to provide you with some value there. In terms of library APIs, how do I talk to server? How do I talk? So if I've got an application that's talking to an HTTP endpoint, as a client, how do I talk to it? Again, nothing, because if you're talking on the semantical level of HTTP as an application protocol, there is no changes. You can still do get, put, post, delete. If you are going lower level, if you are implementing HTTP2, then things change. Then you need to get into the intrinsicals of Netty and stuff like that, and that's not that easy to get into. But if you're doing high level, no change. If you're doing low level, there is a little bit of work to get. So here is, I'll show you some code, for example, for 2 demos here. This is talking to HTTP2. How many of you have used OK HTTP client? Really simple. I just create an HTTP client, create the builder, pass in the URL, say build, and then do a new call on the request, get a response. Okay? If I run this, this is using HTTP 2. And I've not done anything specific, absolutely nothing. The only thing that I did was, as I mentioned, you see here when we run this, it says, welcome to a Go language, you're using HTTP 2 right now, right? Now, to prove that that is the case, let me go to run configuration and select this jar file, which is the ALPN extensions, which I spoke about, which if you're using Java 7 or 8, you need to explicitly put. If you're using 9, you don't. If I remove that and run this, it's going to say you are not an HTTP 2 compliant client. Unfortunately, you're not using HTTP 2 right now. But point being that I need to learn IntelliJ. But apart from that, you see there's no change. Semantically, there's absolutely no change. Now, on the JavaScript side, it's the same thing. So if you're using a JavaScript client, it's the same thing. If the underlying library or whatever you're using supports HTTP 2, there's no semantic change. Now, if I want to get into something more deep like Netty, then yes, I mean, that does change things quite a bit, right? I mean, hold on. What do I have? Let me see here. So, let's see. So there, now you need to know about streams, you need to handle processes, you need to handle priorities. You can get into all of those different aspects, right? And, you know, that is here, you can see I have HTTP 2 somewhere. Where is... So HTTP 2 server, there you go. So yeah, I've got to deal with all of the handshakes for SSL. I've got to deal with processing of the frames, deal with the header frames, everything. But that's if you're doing low level. If you're doing high level, really there is no change. If you're not doing web apps, if you're just HTTP server talking to HTTP client, no change. Nothing, really. Just as long as your application container supports it, you're good to go. Web apps, of course, yes. They do the optimization, but most of that is for the front side, front-end development. Okay? So, now, one thing where you do make some changes, where you can interact even if you're doing high level, is with server push. And with server push, what you can do is two things. Some servers have the ability to configure paths and respond with server push. So for instance, here I have term crashed. So ng HTTP2 server, ng HTTP2 actually has a server, it has a client, it has... I don't know if you can see this, but here what I'm doing is I'm saying you pass a command line parameter to the server that says when the path to do HTML is requested, respond with a server push of CSS bootstrap min.cs. So you can have that level of control with server push. Depending on the server that you're using, it might allow you to configure it via file, via command line, whatever. But some libraries also allow you to programmatically do this. So for instance, if you're using Node.js, there's an HTTP2 server that allows you to programmatically process requests and then respond based on the request with a server push. Jetty also provides this on the Java side. Okay? So that server push is kind of the middle ground between low level and high level kind of thing. Now, it's not all roses, as you know, because not everything is, and it's not a silver bullet, because it is adding somewhat of complexity level to what we already had in terms of HTTP2. If you notice the flow control, the priority of streams, if you want to deal with all of these things, these were basically put away before on the lower level on TCP, and now they're bringing it up on the application level. Dealing with priorities, flow control, etc. How will server push really work? So a lot of you have been using Speedy. You've not been aware of it. HTTP2, now you're aware, and you've been using it. But now that you know of all these features, people will start to use these features more. And we don't know, in the end, how this is going to pan out, because it's still a little bit early in the game. I mean, the RFC was only published in May. Okay? So, as I said, those are some issues with HTTP2, and how they will work in the long run, we don't know. The good news is, though, that if it doesn't work, we'll have HTTP3 to solve all our issues at some point. Okay? And we'll do a thing. So, more information. The best place to start if you want to get more into the details is github.com/HTTP2, where the RFC is on there. Demos are on there, links to all of the different implementations on the Java server side are on there. Everything is like your point of start. There's a very, very good book by Ilya Grigorik, evangelist at Google, that's called High Performance Browser Networking. And while it only has a chapter on one chapter on HTTP2, have you read this book? If you haven't, I highly recommend you read it. It's very, very good, and it explains many things of TCP, HTTP, and if you're doing web development, it's a must-read. And I've got a course that I recently published on Pluralsight, so if you're on Pluralsight, you can see my HTTP2 fundamentals, which expands on these topics and goes into more details with demos, etc. And that's it. Finished a little bit with question time. So any question? Yes, I can. And if you don't have any questions, oh yes.
Anybody work on pushing streams down to TCP?
So the question is, instead of pushing this up to the top, is anyone working? Yes, there is actually. There is a group, but the problem is that it's hard to replace TCP, right? So that's why they're trying to, I mean, if you really think about it, this is to circumvent the issues with TCP, right, while trying to still use the existing infrastructure. I was listening to a talk by Mark Nottingham, who's one of the people on the design committee of HTTP2, and they asked a similar question around that, and he said that there are some initiatives to working on solving TCP in the long run, but I don't know more on that right now. So, yeah. Question?
What protocol is that? You may have mentioned that. What protocol is that using the setup?
HTTP2, so the question is, what protocol is HTTP2 using? Yes, absolutely, still using TCP.
How does it get around the block, basically?
Because it's got a single connection. So the head of line blocking is caused by TCP. Using multiple connections. This is using a single connection. But then it does lead to problems with flow control. Because if one of the streams stops responding for whatever reason, it could potentially lead to a block. So that's why there are ways in which you could kind of control the flow of data. But again, a lot of that hoping is abstracted away from us, developers, at the server levels, right? And then tweaking of the servers, be it Apache, be it IIS, or what have you. So the question is, how is it different from WebSockets? It's completely really different technology. WebSockets is just opening up sockets running on HTTP inside the browser. It serves different purposes. It serves different goals. There's a lot of backlash also against WebSockets. There was an article recently by one of the chaps that works on Stack Overflow and how they'd actually moved away from WebSockets, and now they're mostly using HTTP2. But it's kind of perpendicular, how do you say, to WebSockets. Orthogonal, that's the word. Okay. Perpendicular. Perpendicular. Never mind. I'm sorry, English isn't my first language. Don't know what is, but anyway. Okay, so if you don't have any more questions, thank you. I'll be at the booth, and I have to do publicity. I have a talk tomorrow at 1 p.m., which is Kotlin, the language that we released on Monday, which was yesterday. So if you're interested in that, please join me tomorrow. Thank you.